So we now have to build our embedded AI based application. In the coming videos, we need some tools for it. In this video, we will take a look at the various software and hardware used in this course. Let's first take a look at the hardware used. We have used the ST Microelectronics Nucleo F446RE development board, which will work as our embedded AI device to infer the results by analyzing the G values of X, Y, Z axis coming from the accelerometer sensor via I2C. We are using the ADXL345 accelerometer. And with this, we also need a motor to produce the vibrational data for training and inferring the results on. And in software tools, we need a Windows environment, Anaconda IDE as a Python framework. We need a TensorFlow and Keras installed on the top of Anaconda as a deep learning framework. Then we also need a STM32Cube to generate the C code for hardware abstraction library, drivers, and AI library. We also need Atomic True Studio IDE for compilation, linking, and building the code, and STM32Cube Programmer as a binary flashing tool. So till now we know what we needed to start with this course. In the next video, we will take a look at the introduction of TensorFlow and Keras libraries and how to install them. Thanks for watching. We'll see you in the next lecture. Products to improve the search engine, translation, image capturing, or recommendations. To give a concrete example, Google users can experience a faster and more refined search with AI. If the user types a keyword in the search bar, Google provides a recommendation about what could be the next word. Google wants to use machine learning to take advantage of their massive datasets to give users the best experience ever. Three different groups uses machine learning: researchers, data scientists, and programmers. They can all use the same toolset to collaborate with each other and improve their efficiency. Google does not just only have data, they have the world's most massive computer, so TensorFlow was built to scale on it. It is a library developed by the Google Brain team to accelerate machine learning and deep neural network research. It was built to run on multiple CPUs and GPUs, and even mobile operating systems. It has several wrappers in several languages like Python, C++, or Java. Now let's find out how TensorFlow came into existence. A couple of years ago, deep learning started to outperform than all other machine learning algorithms when giving a massive amount of data. Google saw it could use these deep neural networks to improve its services like Gmail, Photos, and Google search engine. They built a framework called TensorFlow to let researchers and developers work together on an AI model. Once developed and scaled, it allows lots of people to use it. It was first made public in late 2015, while the first stable version appeared in 2017. It is open source under Apache open source license. You can use it, modify it, and redistribute the modified version for a free without paying anything to Google. Next is, how can we use TensorFlow? Basically, the TensorFlow architecture works in three parts. First is pre-processing of the data, then build the model in the programming language you are comfortable with, and then train the model on the available data. It is called TensorFlow because it takes input as a multi-dimensional array, also known as tensors. You can construct a sort of flowchart of operations that you want to perform on that input. The input goes in at one end and then it flows through the system of multiple operations and comes out the other end as an output. This is why it is called TensorFlow, because the tensor goes in it, flows through a list of operations, and then it comes out the other side as an output. And next is, where can TensorFlow run? TensorFlow's hardware and software requirements can be classified into two phases. The first one is development phase. This is when you train the model. Training is usually done on your desktop or laptop. The second is run phase. Once training is done, TensorFlow can be run on many different platforms. You can run it on desktop, running Windows, Mac OS or Linux, or on the cloud as a web services, and can also run on mobile devices like iOS and Android. You can train it on multiple machines, then you can run it on a different machine once you have the trained model. Deep learning relies on a lot of matrix multiplication. TensorFlow is very fast at computing the matrix multiplication because it is written in C++. Although it is implemented in C++, TensorFlow can be accessed and controlled by other languages, mainly Python. Now let's take a look at the components of TensorFlow. There are mainly two components of TensorFlow we need to know about. One is tensor and the second is graph. Let's explore the tensors first. TensorFlow's name is directly derived from its core framework, tensor. In TensorFlow, all the computations involve tensors. A tensor is a vector or matrix of n dimension that represents all types of data. All values in a tensor hold identical data type with a known shape. The next is graph. TensorFlow uses a data flow graph to represent your computation in terms of the dependencies between individual operations. The next is, why is TensorFlow so popular? TensorFlow is the best library of all because it is built to be accessible for everyone. TensorFlow library incorporates different API to build and scale deep learning architectures like CNN or RNN. TensorFlow is based on graph computation. It allows the developers to visualize the construction of the neural network with TensorBoard. This tool is helpful to debug the program. Finally, TensorFlow is built to be deployed and scaled. A TensorFlow attracts the largest popularity on GitHub compared to the other deep learning framework. It is basically built for those people who want to go into the details of the machine learning and want to develop the algorithms from the scratch. Thanks for watching. We'll see you in the next lecture. Learning research and development are Theano and TensorFlow. Both are very powerful libraries, but both can be difficult to use directly for beginners for creating deep learning models. In this video, you will discover the Keras Python library that provides a clean and convenient way to create a range of deep learning models on top of Theano or TensorFlow. Keras is a minimalist Python library for deep learning that can run on top of Theano or TensorFlow. It was developed to make implementing deep learning models as fast and easy as possible for research and development. It runs on Python 2 and 3 and can seamlessly execute on GPUs and CPUs. It is released under the permissive MIT license. Keras was developed and maintained by a Google engineer using 4 guiding principles. Let's go through them one by one. The first one is modularity. According to the concept of modularity, a model can be understood as a sequence. All the concerns of a deep learning model are discrete components that can be combined in an arbitrary ways. The second is minimalism. The library provides just enough to achieve an outcome, no frills and maximizing readability. The third is extensibility. New components are intentionally easy to add and use within the framework, intended for researchers to trial and explore new ideas. The fourth is programming language. No separate model files with custom file formats, everything is native Python. There is a 5-step life cycle to build a neural network model in Keras. The first step is define your network. The second is compile your network. Then third is fit it, and then fourth is to evaluate the network. The fifth is you can use it to make the predictions. Keras is very quick to make a network model. If you want to make a simple network model with a few lines, Keras can help you with that. Look at this example below. It is a simple sequential model which has been written in just 4 lines of code. In the same way as of TensorFlow, we can use the Keras models to train it on a laptop or computer and can run it on a different machine once we have the trained model. And even we can use the end model to run on edge devices which contains microcontrollers in it by converting the model into a C library, which we will gonna do in the next phases of the course. It is the library built for those people who wants to build their machine learning models without going into much details of it. Thanks for watching. We'll see you in the next lecture. Nowadays, the trend is to connect the embedded devices via the internet, collect the data, and run the inference on servers. However, according to the demand of the industry, it would change soon. By using embedded or edgeai, lots of applications can be designed, having features of low cost, low power consumption, low bandwidth, little processing, and secure. Let's have a look at few of them. The first one is early fault prediction and maintenance of machines. According to Industry 4 standard, industry needs a kind of devices for factories which can give feedback about its health status as early as possible to avoid the instant shutdown of the factory. We can analyze the physical parameters like vibration, voltage, current consumption to predict the health status of machine using edgeai technology. It doesn't require any data to send to the cloud and get the inference result back, which makes it power saving, real time, and secure. The next one is security systems. Nowadays, the combination of facial and voice recognition is an excellent method to provide security. By implementing these features on the edge devices, we can design security locks for home, office, and vehicles. These lock systems can infer the voice and face locally, thus we don't need to connect to internet, which makes it more robust and secure. The third one is autonomous vehicles. An autonomous vehicle can make a smart decision by analyzing the surrounding. Images can be analyzed locally on edge devices installed on the car to recognize the traffic lights, pedestrian, road, and people. The fourth one is surveillance and monitoring. By implementing the deep learning models at the edge, any suspicious activities can be monitored in real time. These models are trained to recognize human movements on high-performance computers and later can use the same learning to infer the situation on edge devices. The last one is robots. By implementing the inference on edge, robots can take their decisions independently without a need to connect to the internet. So these can be some of the future products based on the embeddedai. This course will focus on one of the applications to recognize a vibration pattern, which can be used to diagnose any machine containing electric motor, combustible engines, or containing any moving parts. Thanks for watching. We'll see you in the next lecture. And then apply what they have learned to make intelligent decisions. Deep learning is gaining much popularity due to its accuracy when trained with huge amount of data. So the two most popular frameworks for deep learning that we are going to discuss today are Keras and TensorFlow. Now Keras is basically an open source neural network library written in Python. It is also capable of running on top of TensorFlow. It is designed to enable fast experimentation with deep neural networks. It also focuses on being user-friendly, modular, and extensive. Now TensorFlow is an open source library for data flow programming across a range of tasks. It is also a symbolic math library and is used for machine learning applications. These two frameworks are related to each other and perform similar tasks. Let's have a look at the parameters that distinguish them from one another. So the first one is the level of API. Now when we consider the level of API, Keras has a higher level, whereas TensorFlow is basically the framework that provides both high and low level APIs. Keras is a high level API that is capable of running on top of TensorFlow and Theano. It has gained favor for its ease of use and simplicity, facilitating fast development. The next parameter is the speed. Now the speed is comparatively slower in case of Keras, whereas TensorFlow provides a similar pace which is suitable for high performance but gains and computational efficiency of higher performing framework will be outweighed by the fast development environment and the ease of experimentation that Keras offers. Now moving on, the next parameter is the architecture. In the case of architecture, now Keras has a simple architecture. It is more readable and concise. It is simple and easy to use. Most of the beginners prefer to use Keras when compared to the TensorFlow. TensorFlow, on the other hand, is not very easy to use and has a complicated architecture that might not be very helpful for beginners. The next parameter of comparison is an ease of code. Now, one advantage of using Keras is that there is a single line of code for implementing it, which makes the preferable framework for the coders. But TensorFlow provides a reduced size of model along with high accuracy. The next one is debugging. Now in Keras, there is usually very less frequent need to debug simple networks, and it offers a more direct, unconvoluted debugging experience, regardless of the model complexity. But in case of TensorFlow, it is quite difficult to perform debugging. The next parameter is the community support. Now the Keras has got a smaller community support when it comes to troubleshooting any problem. But TensorFlow, on the other hand, is backed by a large community of tech companies. Now moving on to the dataset. Keras is mostly used for small dataset, as it is comparatively slower. Final parameter of comparison includes the popularity. Now all these frameworks have gained a lot of popularity in recent times, but Keras is on the top of the list, followed by TensorFlow. It has gained immense popularity due to its simplicity when compared to the other frameworks. We have seen the various parameters that distinguish the framework, but there is no straight answer to which one is actually better. The choice ultimately comes down to the technical background, needs and expectations. So let's move on and have a look at what are the suitable situations where these frameworks should be used. Keras is mostly preferred in case of rapid prototyping. So if you want to quickly build and test a neural network with minimum lines of code, go for Keras. Also, it is mostly suitable for small size of data and best for newbies as it is simple and easy to understand. Now TensorFlow is mostly preferred for large dataset and also where high performance is mandatory. TensorFlow provides advanced operation and all general purpose functionality for building deep learning models. Thanks for watching. We'll see you in the next lecture. In this lecture, we will take a look at how to install the Keras and TensorFlow libraries. We can use any environment, either Windows or Linux, to install the TensorFlow and Keras, but we have set up the environment on Windows to run it. We can simply install it under the Anaconda IDE, which is famous for scientific computing in Python and R. To install it, simply open the Anaconda prompt and install these libraries using pip command. As mentioned on their official websites, pip is popular package manager in Python used to install various modules. Remember, the pip3 manages the Python 3 packages and pip manages the Python 2 packages. To check the installation is successfully done, simply import these libraries in the Python script. If it throws no error, it means it is successfully installed. In the later videos, we will see how to create a neural network model, to train and infer the vibration pattern using Keras APIs. We have not used the APIs of TensorFlow directly, but to run the Keras APIs, we need the installation of TensorFlow. Thanks for watching. We'll see you in the next Cube and Xcube AI. STM32Cube is an ecosystem for fast software development for STM32 microcontroller. It includes the MCU packages, for instance, STM32Cube F4 containing drivers, low-level APIs, as well as the demo and example codes for Nucleo and Discovery boards. The STM32Cube expansion packages serves as a complement to the MCU packages by offering additional middlewares or drivers. And Xcube AI is the first package in the industry to enable the conversion of a neural network into the optimized code for STM32 MCUs, which is also integrated in the STM32 cube. It contains the almost all layers which are necessary to implement a neural network, like convolution layer, dense layer, sigmoid activation functions, softmax activation functions, and many more. It supports various deep learning platforms like Keras, TensorFlow, Caffe, Lasagne, so the developer can generate, write, and compile the code on a single platform for STM32 controllers. We will use STM32 Cube during the development of our project. You can download and install it from the ST Microelectronics website. We will learn in later videos how to create a project inside the STM32 Cube and how to convert a neural network model generated by a Keras to C library for STM32 microcontrollers. Thanks for watching. We'll see you in the next lecture. Hi, welcome back guys. We will look at the development board we have used. We have used the very famous ST Microelectronics Nucleo board known as Nucleo F446RE. It contains 64-pin microcontroller with 512 KB ROM and 128 KB RAM. The STM32 F446RE devices are based on the high-performance ARM Cortex-M4 32-bit RISC core, operating at a frequency of up to 180 MHz. It also contains the DSP engine with floating point unit and CRC calculator. The controller with these specifications are good enough to run the complex math functions inside the neural network library generated via the Xcube AI extension present in STM32 Cube, as we discussed in the previous lecture. With this, we will use I2C pins of the controller to interface to our accelerometer module and UART pins to communicate to our PC. Thanks for watching. We'll see you in the next lecture. So train the machine using data which is well labeled. That means some data is already tagged with correct answer. After that, machine is provided with new set of examples or data, so that supervised learning algorithm analyzes the training data and produces the correct outcome from labeled data. For instance, suppose you are given a basket filled with different kinds of fruits. Now, the first step is to train the machine with all different fruits one by one, like this. If shape of object is rounded and having color red, then it will be labeled as apple. If shape of the object is long, curving cylinder having color green or yellow, then it will be labeled as banana. Now suppose after training the data, you have given a new separate fruit, say banana, from basket and asked to identify it. Since machine has already learned the things from previous data and this time have to use it wisely, it will first classify the fruit with its shape and color and would confirm the fruit name as banana and put it in the banana category. The machine learns the things from training data and then apply the knowledge to test data. Supervised learning classified into two categories of algorithms. The classification. A classification problem is when the output variable is a category, such as red or blue, or disease and no disease. The second is regression. A regression problem is when the output variable is a real value, such as dollars or weight. Thanks for watching. We'll see you in the next lecture. Neither classified nor labeled, and allowing the algorithm to act on that information without any guidance. Here the task of machine is to group unsorted information according to similarities, patterns, and differences without any prior training of data. Unlike supervised learning, no teacher is provided. That means no training will be given to the machine. Therefore, machine is restricted to find the hidden structure in unlabeled data by itself. For instance, suppose it is given an image having both dogs and cats which have not seen ever. The machine has no any idea about the features of dogs and cats. So we cannot categorize it in dogs and cats, but it can categorize them according to their similarities. patterns, and differences. That is, we can easily categorize the above picture into two parts. First part may contain all pics having dogs in it, and the second part may contain all pics having cats in it. Here you didn't learn anything before, means no training data or examples. Unsupervised learning classified into two categories of algorithms. First is clustering. A clustering problem is where you want to discover the inherent groupings in the data, such as grouping customers by purchasing behavior. The second is association. An association learning problem is where you want to discover rules that describe large portion of your data, such as people that buy X also tend to buy Y. Thanks for watching. We'll see you in the next lecture. Real neuron present in the human mind. The neuron in the human brain looks something like this. It contains some kind of soma, dendroids, axon kind of things. Let's take an example of an eye firing neurons in the brain. Whenever human eye is exposed to the light in the environment, it triggers neurons in the retina to fire, which sends electrical signals into the brain's vision centers, by which our brain recognizes the object through which the light has been reflected to our eyes. On the other hand, an artificial neuron is basically a mathematical formula which gets an input x and multiply it by a weight set in the connection from one neuron to the other. This x input can be from external sensors or can be a pixel value from the camera, and the weights are adjusted in such a way during the training of the neural network so it can predict the output accurately. The single artificial neuron will do a dot product between w and x and then add a bias. The result is passed to an activation function that will add some non-linearity to it to get a discrete output. If we want to think upon a neurons in our computers, then we can say it's just a number stored in the variables, or more precisely we can say the numbers stored in the computer memory, to which we call weights and biases. They change their values according to the mathematical calculation performed on the input values while training them with the external data. Once trained, whenever a new input is given to the neuron, it performs calculation based on the weights and biases it has stored previously and gives out the output result. The neural network will be formed by these artificial neurons, which we will discuss in the next lecture. Thanks for watching. We'll see you in the next lecture. Neural network is the structure of interconnected neurons divided into various layers by which the information flows from the input to the output layer via some hidden layers. Each connection between neurons transmits a signal from one neuron to the other. The receiving neuron processes the signal and signals to downstream neurons connected to it within the network. Note that neurons are also commonly referred to as nodes. The structure of the artificial neural network is same as of the structure of the neuron in our brain. That's why they are also known as artificial neural networks, and sometimes we use the word deep neural network. In deep neural network, whenever there is more than one hidden layer in an artificial neural network, then we call it deep neural network. Let's take an example of a neural network. It is basically comprised of three layers: input layer, hidden layers, and output layer. The input layer recognizes the various input patterns, and those patterns are filtered via the hidden layers. And finally, it activates the neurons present in the output layer. Let's assume the input layer is recognizing length parameter, and the output layer will give the output as a big or small on the output layer. All the recognition is based on the mathematical calculation between the various layers. The non-linearity will allow different variations of an object of the same class to be learned separately. More neurons and more layers is always better, but it will need more data to train. Each layer learns a concept from its previous layer, so it's better to have deeper neural networks than the wide one. And it took 20 years to discover this. In brief, we can say An artificial neural network is a computing system that is comprised of a collection of connected units called neurons that are organized into what we call layers, and when layers are more than one, we call it deep artificial neural network. Thanks for watching. We'll see you in the next lecture. Pooling layer, dropout layer, batch normalization layer, and so on. But the question is why we have different types of layers. Different layers perform different transformations on their inputs, and some layers are better suited for some tasks than others. For example, a convolution layer is usually used in models that are doing work with image data. Recurrent layers are used in models that are doing work with time series data. For now, we will keep our focus on layers in general, and we will learn more in depth about specific layer types as we dig deeper into the deep learning. Let's take an example of artificial neural network. As we can see that the first layer, the input layer, consists of 16 nodes. Each of the 16 nodes in this layer represents an individual feature from a given sample in our dataset. This tells us that a single sample from our dataset consists of 16 dimensions. When we choose a sample from our dataset and pass this sample to the model, each of the 16 values contained in the sample will be provided to a corresponding node in the input layer. As we can see that each of the 16 input nodes are connected to every node in the next layer. Each connection between the first and second layers transfers the output from the previous node to the input of the receiving node. The two layers in the middle that have 12 and 10 nodes respectively are hidden layers. Simply, they are positions between the input and output layers. The next is layer weights. Each connection between two nodes has an associated weight, which is just a number. Each weight represents the strength of the connection between the two nodes. When the network receives an input at a given node in the input layer, this input is passed to the next node via a connection, and the input will be multiplied by the weight assigned to that connection. We have already discussed about it while discussing about the neurons. For each node in the second layer, a weighted sum is then computed with each of the incoming connections by adding a bias to it. We will also discuss about the bias in the later videos in detail. The sum is then passed to an activation function which performs some type of transformation on the given sum. For example, an activation function may transform the sum to be a number between 0 and 1. The actual transformation will vary depending on which activation function is used. We will discuss about activation functions in later videos. Next is forward pass through a neural network. Once we obtain the output for a given node, the obtained output is the value that is passed as input to the nodes in the next layer. This process continues until the output layer is reached. The number of nodes in the output layer depends on the number of possible output or prediction classes we have. In our example, we have 5 possible prediction classes. Suppose our model was trained with classifying 5 types of numbers from an image. Each node in the output layer would represent one of the 4 possibilities. For example, we could have 1, 2, 3, 4, and 5 as an image. The categories or classes depends on how many classes are in our dataset. For a given sample from the dataset, the entire process from input layer to the output layer is called a forward pass through a network. As the model learns, the weights at all connections are updated and optimized so that the input layer point maps to the correct output prediction class. Thank you guys. We'll see you in the next lecture. This nonlinear function is called activation function. In an artificial neural network, an activation function is a function that maps a node's input to the corresponding output. In the previous video, we took the weighted sum of each incoming connections for each node in the layer and passed that weighted sum to an activation function. The activation function does some type of operation to transform the sum to a number that is oftentimes between some lower limit and some upper limit. This transformation is known as nonlinear transformation. Now let's find out what an activation function do and how this concept came into existence. Well, an activation function is biologically inspired by activity in our brains, where different neurons fire by different stimuli. For example, if you see any color, suppose green, some neurons which recognize the green color will be activated in our brain. If you see another color like yellow, this will cause another neurons in your brain to fire. Deep within our brains, certain neurons are either firing or they are not. This can be represented by a 0 for not firing or a 1 for firing. So to mimic the same functionality of the brain, activation functions was made. An important feature of linear functions is that the composition of two linear functions is also a linear function. This means that even in very deep neural networks, if we only had linear transformations of our data values during a forward pass, the learned mapping in our network from input to the output would also be linear. Typically, the types of mappings that we are aiming to learn with our deep neural networks are more complex than simpler neural mappings. This is where activation functions come in. Most activation functions are non-linear, and they are chosen in this way on purpose. Having non-linear activation functions allow our neural networks to compute arbitrarily complex functions. Now let's look at some examples of activation functions. The first is ReLU activation function. ReLU, which is short for rectified linear unit, transforms the input to the maximum of the either 0 or the input itself. So if the input is less than or equal to 0, then ReLU will output 0. If the input is greater than 0, ReLU will then just output the given input. The idea here is the more positive the neuron is, the more activated it is. The next is sigmoid activation function. For negative inputs, sigmoid will transform the input to a number close to 0. For positive inputs, sigmoid will transform the input into a number close to 1. For inputs close to 0, sigmoid will transform the input into some number between 0 and 1. So for sigmoid, 0 is the lower limit and 1 is the upper limit. Now we have only talked about two activation functions here, sigmoid and ReLU. But there are other types of activation functions that do different types of transformations to their inputs. So briefly, we can say we use activation functions on weighted sum of inputs, including their bias, to get non-linear output. Thanks for watching. We'll see you in the next lecture. Position of a moving object with respect to time is the object's velocity. Now the gradient is a multivariable generalization of a derivative. Derivative of a function of a single variable is a scalar valued function. However, the gradient of a function of several variables is a vector valued function, which means gradient tells us the change of a function with direction of change. Now, if we see the word gradient descent, gradient means change in some function in a particular direction, and descent means moving in falling or downward direction. So, the gradient descent is an optimization algorithm used to minimize some function by continuously moving in the direction of sharply falling direction. Sharply falling means negative of a gradient. In machine learning, we use gradient descent to update the parameters of our model in the direction of minimum loss, and gradient descent tells us the direction of minimum loss. Parameters refer to coefficients in linear regression and weights in neural networks. Let's discuss about the cost function. A loss function tells us how good our model is at making prediction for a given set of parameters. The loss function computes the error for a single training example, while the cost function is the average of the loss functions of the entire training set. The cost function has its own curve and its own gradients. The slope of this curve tells us how to update our parameters to make the model more accurate. Consider the image below in the context of a cost function. Our goal is to move from a mountain in the top to the blue sea in the bottom left. The arrows represents the direction of falling sharply, or the other word we can use is in the direction of negative gradient from any given point, the direction that decreases the cost function as quickly as possible. Starting at the top of the mountain, we take our first step downhill in the direction specified by the negative gradient. Next, we recalculate the negative gradient and take another step in the direction it specifies. We continue this process iteratively until we get to the bottom, or to a point where we can no longer move downhill, means a local minima. Next is learning rate. The size of these steps is called the learning rate. With a high learning rate, we can cover more ground each step, but we risk overshooting the lowest point since the slope of the hill is constantly changing. With a very low learning rate, we can confidently move in the direction of the negative gradient since we are recalculating it so frequently. A low learning rate is more precise, but calculating the gradient is time consuming, so it will take us a very long time to get to the bottom. Thanks for watching. We'll see you in the next lecture. What does it mean by the training of the neural network? When we feed the data to our neural network while training, we are basically trying to solve an optimization problem. We are trying to optimize the weights within the model. Our task is to find out the weights that most accurately map our input data to the correct output class. This mapping is what the neural network must learn. Each connection between nodes has an arbitrary weights assigned to it. During training, these weights are iteratively updated and moved towards their optimal values. The weights are optimized using what we call an optimization algorithm. The optimization process depends on the chosen optimization algorithm. We also use the term optimizer to refer to the chosen algorithm. The most widely known optimizer is called stochastic gradient descent, or more simply SGD. There is one more known as ADAM. When we have any optimization problem, we must have an optimization objective. So now let's consider what SGD's objective is in optimizing the model's weights. The objective of SGD is to minimize some given function that we call a loss function. So SGD updates the model's weights in such a way as to make this loss function as close to its minimum value as possible. One common loss function is mean squared error, but there are several loss functions that we could use in its place. As deep learning practitioners, it's our job to decide which loss function to use. For now, let's just think of general loss function. Later we will look at specific loss functions in more detail. Alright, but what is the actual loss we are talking about? Well, during training we supply our model with data and the corresponding labels to that data. For example, suppose we have a model that we want to train to classify whether images are either images of mobile phones or images of television. We will supply our model with images of mobile phones and television along with the labels for these images that state whether each image is of a mobile or of a television. Suppose we give one image of a mobile phone to our model. Once the forward pass is complete and the mobile phone image data has flowed through the network, the model is going to provide an output at the end. This will consist of what the model thinks the image is, either a mobile phone or a television. In a literal sense, the output will consist of probabilities for mobile phone or television. For example, it may assign a 70% probability to the image being a mobile phone and a 30% probability to being a television. In this case, the model is assigning a higher likelihood to the image being of a mobile phone than of a television. If we stop and think about it for a moment, this is very similar to how humans make decisions. Everything is a prediction. The loss is the error or difference between what the network is predicting for the image versus the true label of the image. And SGD will try to minimize this error to make our model as accurate as possible in its predictions. After passing all of our data through our model, we are going to continue passing the same data over and over again. This process of repeatedly sending the same data through the network is considered training. During this training process is when the model will actually learn. We will discuss about the training of neural network, SGD and loss more in detail in the coming videos. Thanks for watching. We'll see you in the next video. It's called a forward pass, and the resulting output depends on the weights at each connection inside the network. Once all the data points in our dataset have been passed through the network, we say that an epoch is complete. An epoch refers to a single pass of the entire dataset to the network during training. Keep this word in mind, we will use it in the later videos. Note that many epoch occurs throughout the training process as the model learns. So what exactly does it mean for the model to learn? Whenever the model is initialized, the network weights are set to arbitrary values. We have also seen that at the end of the network, the model will provide the output for a given input. Once the output is obtained, the loss can be computed for that specific output by looking at what the model predicted versus the true label. The loss computation depends on the chosen loss function. After the loss is calculated, the gradient of this loss function is computed with respect to each of the weights within the network. Note the gradient is just a word for the derivative of a function of several variables, which tells us in which direction the loss is going. As of now, let's focus in on only one of the weights in the model. At this point, we have calculated the loss of a single output, and we calculate the gradient of that loss with respect to our single chosen weight. This calculation is done using a technique called backpropagation. Once we have the value for the gradient of the loss function, we can use this value to update the model's weights. The gradient tells us which direction will move the loss towards the minimum, and our task is to move in the direction that lowers the loss and steps closer to the minimum value. We then multiply the gradient value by something called a learning rate. A learning rate is a small number usually ranging between 0.01 and 0.0001, but the actual value can be varied. The learning rate tells us how large of a step we should take in the direction of the minimum. Just keep this in mind for now, and we will more closely look at the learning rates in the future videos. Alright, so we multiply the gradient with the learning rate, and we subtract this product from the weight, which will give us the new updated value for this weight. In this discussion, we just focused on one single weight to explain the concept, but this same process is going to happen with each of the weights in the model, each time data pass through it. The only difference is that when the gradient of the loss function is computed, the value for the gradient is going to be different for each weight because the gradient is being calculated with respect to each weight. So now imagine all these weights being iteratively updated with each epoch. The weights are going to be incrementally getting closer and closer to their optimized values while SGD works to minimize the loss function. This updating of the weights is essentially what we mean when we say that the model is learning. It's learning what values to assign to each weight based on how those incremental changes are affecting the loss function. As the weights change, the network is getting smarter in terms of accurately mapping inputs to the correct output. Alright, now with the explanation along with our last video on training, we should now have a general idea about what it means to train a model and how the model learns through this training process. Thanks for watching, we'll see you in the next lecture. SGD is attempting to minimize by iteratively updating the weights in the network. At the end of each iteration or epoch, during the training process, the loss will be calculated using the network's output predictions and the true labels for the respective input. Suppose our model is classifying images of mobile phone and television, and assume that the label for mobile phone is 5 and the label for the television is 6. Now suppose we pass an image of a mobile phone to the model and the provided output is 5.35. In the case the difference between the model's prediction and the true label is 5.35 minus 5 is equal to 0.35. This difference is called error. This process is performed for every output. For each epoch, the error is accumulated across all individual outputs. Let's look at loss functions that is commonly used in practice called mean squared error. For a single sample with MSE, we first calculate the difference between the provided output prediction and the label. We then square this error. For a single input, this is all we do. If we passed multiple samples to the model at once, then we would take the mean of the squared errors over all these samples. This was just illustrating the math behind how one loss function works. There are several different loss functions that we could work with though. The general idea that we just showed for calculating the error for individual samples will hold true for all of the different types of loss functions. The implementation of what we actually do with each of the errors will be dependent upon the algorithm of the given loss function we are using. For example, we average the squared errors to calculate MSE, but other loss functions will use other algorithms to determine the values of the loss. If we passed our entire training set to the model at once, then the process we just went over for calculating the loss will occur at the end of each epoch during training. If we split our training set into batches and passed batches one at a time to our model, then the loss would be calculated on each batch. Since the loss depends on the weights, we expect to see the values of the loss change each time the weights are updated. Given that the objective of SGD is to minimize the loss, we want to see our loss decreases as we run more epochs. Thanks for watching. We'll see you in next lecture. In the previous videos, an epoch is one iteration of training a neural network with the available dataset. So during each epoch, our model will be trained over and over again on this same data in our training set, and it will continue to learn about the features of this data. The hope with this is that later we can deploy our model and have it accurately predict on new data that it has never seen before. It will be making these predictions based on what it has learned about the training data. Okay, now let's discuss the validation set. The validation set is the set of data separate from the training set that is used to validate our model during training. This validation process helps give information that may assist us with adjusting our hyperparameters. Recall how we just mentioned that with each epoch during training, the model will be trained on the data in the training set. Well, it will also simultaneously be updated on the data in the validation set. We know from our previous video on training that during the training process, the model will be classifying the output for each input in the training set. After this classification occurs, the loss will then be calculated, and the weights in the model will be adjusted. Then during the next epoch, it will classify the same input again. Now also during training, the model will be classifying each input from the validation set as well. It will be doing this classification based only on what it has learned about the data it is being trained on in the training set. The weights will not be updated in the model based on the loss calculated from our validation data. Remember, the data in the validation set is separate from the data in the training set. So when the model is validating on this data does not consist of samples that the model already is familiar with from training. One of the major reasons we need a validation set is to ensure that our model is not overfitting to the data in the training set. We will discuss overfitting and underfitting in detail in the later videos. But the idea of overfitting is that our model becomes really good at being able to classify data in the training set, but it is unable to generalize and make accurate classifications on data that it was not trained on. During training, we are also validating the model on the validation set and see that the results it's giving for the validation data are just as good as the results it is giving for the training data. Then we can be more confident that our model is not overfitting. The validation set allows us to see how well the model is generalizing during training. On the other hand, if the results on the training data are really good, but the results on the validation data are lagging behind, then our model is overfitting. Now let's move on to the test set. The test set is the set of data that is used to test the model after the model has already been trained. The test set is separate from both the training set and the validation set. After our model has been trained and validated using our training and validation set, we will then use our model to predict the output of the unlabeled data in the test set. One major difference between the test set and the two other sets is that the test set should not be labeled. The training set and the validation set have to be labeled so that we can see the matrices given during training, like the loss and the accuracy from each epoch. When the model is predicting on unlabeled data in our test set, this would be the same type of process that would be used if we were to deploy our model into the field. The test set provides a final check that the model is generalizing well before deploying the model to production. For example, if we are using a model to classify data without knowing what the labels of the data are beforehand, or with never have been shown the exact data it is going to be classifying, then of course we wouldn't be giving our model labeled data to this. The entire goal of having a model to be able to classify is to do it without knowing what the data is beforehand. The ultimate goal of machine learning and deep learning is to build models that are able to generalize well. Now we have an idea about how our data should be organized in terms of datasets and how each of these datasets are used. The main reason for having the three separate datasets is to ensure that the model is able to generalize by predicting accurately on unseen data. When the model is failing to generalize, we are usually in a situation of overfitting or underfitting. Thanks for watching. We'll see you in next lecture. Let's build more on the concept now. Overfitting occurs when our model becomes really good at being able to classify or predict on data that was included in the training set, but is not as good as classifying data that it was not trained on. So essentially the model has overfit the data in the training set. But the question is how to spot the overfitting. We can tell if the model is overfitting based on the matrices that are given for our training data and validation data during training. We previously saw that when we specify a validation set during training, we get matrices for the validation accuracy and loss, as well as the training accuracy and loss. If the validation matrices are considerably worse than the training matrices, then that is the indication that our model is overfitting. We can also get an idea that our model is overfitting if during training the model's matrices were good, but when we use the model to predict on test data, it doesn't accurately classify the data in the test set. The concept of overfitting boils down to the fact that the model is unable to generalize well. It has learned the features of the training set extremely well. But if we give the model any data that slightly deviates from the exact data used during training, it is unable to generalize and accurately predict the output. Overfitting is an incredibly common issue. How can we reduce it? There are some techniques presented to reduce the overfitting. Let's discuss them one by one. The first is adding more data to the training set. The easiest thing we can do, as long as we have access to it, is to add more data. The more data we can train our model on, the more it will be able to learn from the training set. Also, with more data, we are hoping to adding more diversity to the training set as well. For example, if we train our model to classify whether an image is mobile phone or television, and we have shown only the pictures of the modern television, then it may have difficulty to recognize the older series of the television. To generalize it, if we add more data to this model to detect more varieties, then our model data will become more diverse and model will be less likely to overfit. Another technique we can deploy to reduce overfitting is to use data augmentation. This is the process of creating additional augmented data by reasonably modifying the data in our training set. For image data, for example, we can do these modifications by cropping, rotating, flipping, and zooming. The general idea of data augmentation allows us to add more data to our training set that is similar to the data that we already have, but is just reasonably modified to some degree or so that it is not the exact same. For example, if most of our mobile phone images were facing to the left, then it would be reasonable modification to add augmented flipped images so that our training set would also have mobile phones that face to the right. Something else we can do to reduce overfitting is to reduce the complexity of our model. We could reduce complexity by simply making changes like removing some layers from the model or reducing the number of neurons in the layers. This may help our model generalize better to data it has not seen before. The last tip we will cover for reducing overfitting is to use something called dropout. The general idea behind dropout is that if you add it to a model, it will randomly ignore some subsets of nodes in a given layer during training. That is, it drop out the nodes from the layer, hence the name dropout. This will prevent these dropped out nodes from participating in producing a prediction on the data. This technique may also help our model to generalize better to data it has not seen before. We will cover the full concept of dropout as a regularization technique in another video, and there we will understand why this makes sense. Hopefully now we understood the concept of the overfitting, why it occurs and how we can reduce it if we see it happening in our model. In the next video we will explore the concept of underfitting. Thanks for watching, we'll see you in this video. We have learned that an overfitting to be an issue that occurs when our model is able to predict on data it was trained on really well, but is unable to generalize and accurately predict on data it has not seen before. Underfitting is on the opposite end of the spectrum. A model is said to be underfitting when it is not able to classify the data it was trained on. We can tell that a model is underfitting when the matrices given for the training data are poor, meaning that the training accuracy of the model is low and the training loss is high. If the model is unable to classify data it was trained on, it's unlikely not going to do well at predicting on data that it has not seen before. So now that we know that underfitting is, how can we reduce it? One thing we can do is increase the complexity of our model. This is the exact opposite of the technique we gave to reduce overfitting. If our data is more complex and we have a relatively simple model, then the model may not be sophisticated enough to be able to accurately classify or predict on our complex data. We can increase the complexity of our model by doing things such as increasing the number of layers in the model, increasing the number of neurons in each layer, changing what type of layers we are using and where. Another technique we can use to reduce underfitting is to add more features to the input samples in our training set, if we can. These additional features may help our model classify the data better. For example, say we have a model that is attempting to predict the television. As we know, there are various types of varieties of television. If we need to generalize our model to predict the every varieties, then we need to show the image of a television from each variety to our model. And then perhaps this may help our model learn more about the data and improve its accuracy. The last tip we will discuss about reducing underfitting is to reduce dropout. Again, this is exact opposite of a technique we gave in a previous video for reducing overfitting. As mentioned in the video, dropout, which we will cover in more detail at a later time, is a regularization technique that randomly ignores a subset of nodes in a given layer. It essentially prevents these dropped out nodes from participating in producing a prediction on the data. When using dropout, we can specify a percentage of the nodes we want to drop. So if we are using a 25% dropout rate and we see that our model is underfitting, then we can decrease our amount of dropout by reducing the dropout percentage to something lower than 25 and see what type of matrices we get when we attempt to train again. These nodes are only dropped out for purpose of training and not during validation. So if we see that our model is fitting better to our validation data, then this is a good indicator to reduce the amount of dropout that we are using. Hopefully now we understood the concept of underfitting, why it happens and how can we reduce it. We will see it happening in our models. In the next video, we will take a look at the regularization in a neural network. Thanks for watching. We'll see you in the next lecture. Neural network to learn, we briefly mentioned the learning rate as a number that we multiply our resultant gradient by. Let's go more into that idea now. We know that the objective of during training is for SGD to minimize the loss between the actual output and the predicted output from our training samples. The path towards this minimized loss is occurring over several steps. Recall that we started the training process with arbitrarily set weights, and then we incrementally update these weights as we move closer and closer to the minimized loss. Now the size of these steps we are taking to reach our minimized loss is going to depend on the learning rate. Conceptually, we can think of the learning rate of our model as a step size. Before going further, let's first pause for a quick refresher. We know that during training, after the loss is calculated for our inputs, the gradient of that loss is then calculated with respect to each of the weights in our model. Once we have the value of these gradients, this is where the idea of our learning rate comes in. The gradients will then get multiplied by the learning rate. This learning rate is a number usually ranging between 0.01 and 0.0001. But the actual value can vary, and any value we get for the gradient is going to become pretty small once we multiply it by the learning rate. Alright, so we got the value of this product for each gradient multiplied by the learning rate, and we then take each of these values and update the respective weights by subtracting this value from them. We reach the previous weights that were set on each connection and update them with these new values. The value we choose for the learning rate is going to require some testing. The learning rate is another one of those hyperparameters that we have to test and tune with each model before we know exactly where we want to set it. But as mentioned earlier, a typical guideline is to set it somewhere between 0.01 and 0.0001. When setting the learning rate to a number on the higher side of this range, we risk the possibility of overshooting. This occurs when we take a step that's too large in the direction of the minimized loss function and shoot past this minimum and miss it. To avoid this, we can set the learning rate to a number on the lower side of this range. With this option, since our steps will be really small, it will take us longer to reach the point of minimized loss. Overall, the act of choosing between a higher learning rate and a lower learning rate leaves us with this kind of trade-off idea. Alright, so now we should have an idea about what the learning rate is and how it fits into our process of training. Thanks for watching. We'll see you in the next lecture. In this video on how an artificial neural network learns, we saw that when we train our model, we have to specify a batch size. Let's go ahead and discuss the details about this now. The batch size is the number of samples that will be passed through the network at one time. Note that a batch is also commonly referred to as a mini batch. The batch size is the number of samples that are passed to the network at once. Now recall that an epoch is one single pass over the entire training set to the network. The batch size and epoch are not the same thing. Let's illustrate this with an example. Let's say we have 500 images of mobile phone that we want to train our network on in order to identify different types of mobiles. Now let's say we specify our batch size to be 10. This means that 10 images of mobile phone will be passed as a group or as a batch at one time to the network. Given that a single epoch is one single pass of all the data through the network, it will take 50 batches to make up a full epoch. We have 500 images divided by the batch size of 10, which equals 50 total batches. A batches in epoch is equal to training set size divided by the batch size. Okay, we have the idea of batch size down now, but what is the point? Why not just pass each data element one by one to our model, rather than grouping the data in batches? Well, for one, generally the larger the batch size, the quicker our model will complete each epoch during training. This is because, depending on our computational resources, our machine may be able to process much more than one single sample at a time. The trade-off, however, is that even if our machine can handle very large batches, the quality of our model may degrade as we set our batch larger, and may ultimately cause the model to be unable to generalize well on data it hasn't seen before. In general, batch size is another one of the hyperparameters that we must test and tune based on how our specific model is performed during training. This parameter will also have to be tested in regards to how our machine is performing in terms of resource utilization when using different batch sizes. For example, if we were to set our batch size to a relatively higher number, say 100, then our machine may not have enough computational power to process all 100 images in parallel. and this would suggest that we need to lower our batch size. Thanks for watching. We'll see you in the next lecture. This could be applied in a problem of recognizing mouse. Fine-tuning is a way of applying or utilizing transfer learning. Specifically, fine-tuning is a process that takes a model that has already been trained for one given task and then tunes or tweaks the model to make it perform a second similar task. But the question is, why use fine-tuning? Assuming the original task is similar to the new task, using an artificial neural network that has already been designed and trained allows us to take advantage of what the model has already learned without having to develop it from scratch. When building a model from scratch, we usually must try many approaches through trial and error. For example, we have to choose how many layers we are using, what type of layers we are using, what order to put the layers in, how many nodes to include in each layer, decide how much regularization to use, what to set our learning rate as, etc. Number of layers, types of layers, order of layers, number of nodes in each layer, how much regularization to use, learning rate. Building and validating our model can be a huge task in its own, right? Depending on what data we are training it on. This is what makes the fine-tuning approach so attractive if we can find a trained model that already does one task well. And that task is similar to ours in at least some remote way. Then we can take advantage of everything the model has already learned and apply it to our specific task. Now, of course, if the two tasks are different, then there will be some information that the model has learned that may not apply to our new task. Or there may be new information that the model needs to learn from the data regarding the new task that wasn't learned from the previous task. For example, a model is trained on mouse is not going to have ever seen a cat. So this feature is something new the model would have to learn about. However, think about everything our model for recognizing cat could use from the model that was originally trained on mouse. This already trained model has learned to understand edges and shapes and textures are more objectively eyes, ears, legs, color, etc. All of these learned features are definitely things we could benefit from in our new model for classifying cats. So this sounds fantastic, right? But how do we actually technically implement this? Going back to the example we just mentioned, if we have a model that has already been trained to recognize mouse and we want to fine-tune this model to recognize cat, we can first import our original model that was used on the mouse problem. For simplicity purposes, let's say we remove the last layer of this model. The last layer would have previously been classifying whether an image was a mouse or not. After removing this, we want to add a new layer back that's purpose is to classify whether an image is a cat or not. In some problems, we may want to remove more than just the last single layer, and we may want to add more than just one layer. This will depend on how similar the task is for each of the models. Layers at the end of our model may have learned features that are very specific to the original task, whereas layers at the start of the model usually learn more general features like edges, shapes, and textures. After we have modified the structure of the existing model, we then want to freeze the layers in our new model that came from the original model. By freezing, we mean that we don't want the weights for these layers to update whenever we train the model on our new data for our new task. We want to keep all of these weights the same as they were after being trained on the original task. We only want the weights in our new or modified layers to be updating. After we do this, all that's left is just to train the model on our new data. Again, during this training process, the weights from all the layers we kept from our original model will stay the same, and only the weights in our new layers will be updating. At this point, we should have a good idea about what transfer learning and fine-tuning of a neural network is, and why it's useful. Thanks for watching. We'll see you in the next lecture. Result. So, convolution of a, b is equal to the convolution of b comma a. In this case, consider that the blue signal f of t is our input signal and g of t is our kernel. The term kernel is used when you use convolutions to filter signals. Now let's discuss 1D convolution. In the case of 1D convolution, the output size is calculated with this formula, where output size is equal to input size minus kernel size plus 1. Now let's take a look at the application of convolution. People generally use convolution on signal processing for the following use cases: to filter the signals in 1D audio and 2D image processing, to check how much the signal is correlated to another, and to find patterns in the signals. To understand better the concept of convolution, let's do an example. Basically, we are going to convolve two signals, x and w. The first thing is to flip w horizontally or rotate to left 180 degrees. After that, we need to slide the flipped w over the input x. Observe that on steps 3, 4 and 5, the flipped window is completely inside the input signal. Those results are called valid convolutions. The cases where the flipped window is not fully inside the input window x, we can consider to be 0 or calculate what is possible to be calculated. For example, on step 1, we multiply 1 by 0 and the rest is simply ignored. Next is input padding. In order to keep the convolution result size the same size as the input and to avoid an effect called circular convolution, we pad the signals with 0. Where you put the zeros depends on what you want to do. That is, on 1D case, you can concatenate them on each end, but on 2D, it is normally placed all the way around the original signal. The next is transforming convolution to computational graph. In order to calculate partial derivatives of every node's inputs and parameters, it's easier to transform the operations to a computational graph. Here I am going to transform the previous 1D convolution, but this can be extended to 2D convolution as well. Here our graph will be created on the valid cases where the flipped kernel will be fully inserted on our input window. We use this graph to infer the gradients of the inputs x and weights w of the convolution layer. Now we extend to second dimension. 2D convolution are used as image filters. And when you would like to find a specific patch on an image, an example of filtering is below. The first is doing by hand. First we should flip the kernel, then slide the kernel on the input signal. Before doing this operation by hand, check out the animation showing how this sliding works. The next is stride. By default, when we are doing convolution, we move our window 1 pixel at a time. But sometimes in convolutional neural networks, we want to move more than 1 pixel. For example, on pooling layers with kernels of size 2, we will use a stride of 2. Setting the stride and kernel size both to 2 will result in the output being exactly half the size of the input along both dimensions. Observe that below the red kernel window is moving much more than 1 pixel at a time. It is useful to know what the dimension of our outputs are going to be after we have performed some convolution operations to it. Luckily, there is a handy formula that tells us exactly that. If we consider convolving an input of spatial-sized h and w padded by p with a square kernel of size f and using stride s, then the output size of convolution is defined as output size of w is equal to w minus f plus 2p divided by s plus 1. The output size of h is equal to h minus f plus 2p divided by s plus 1. F is the size of the kernel. Normally we use square kernels, so f is both the width and height of the kernel. Next is implementing convolution operation. The example below will convolve a 5 into 5 into 3 input with a convolution layer with the parameters stride is equal to 2, pad is equal to 1, and f is equal to 3, and k is equal to 2. Our input has 3 channels, so we need a 3 into 3 into 3 kernel weights. We have two filters, so we will have two output activations at the end. Also, we can calculate the size of these two outputs to be 5 minus 3 plus 2 divided by 2 plus 1 is equal to 3. So we will get a final output volume of size 3 into 3 into 2. Thanks for watching. We'll see you in the next lecture. That are learned so that these filters are adjusted automatically to extract the most useful information for the task at hand without feature selection. Convolution neural networks are better to work with images. Normal neural networks does not fit well on image classification problems. The most important operation on the convolution neural network are the convolution layers. Imagine a 32 by 32 by 3 image. If we convolve this image with a 5 by 5 by 3, the result will be an activation map of 28 by 28 by 1. The filter will look for a particular thing on all the image. This means that it will look for a pattern in the whole image with just one filter. Now consider that we want our convolution layer to look for 6 different things. In this case, our convolution layer will have 6 5 by 5 by 3 filters, each one looking for a particular pattern on the image. By the way, the convolution by itself is a linear operation. If we don't want to suffer from the problem of a linear classifier, we need to add at the end of the convolution layer a non-linear layer. Normally we use ReLU layer, which is known as rectified linear output. Another important point of using convolution as pattern match is that the position where the thing that we want to search on the image is irrelevant. In the case of neural networks, the model will learn an object on the exact location where the object is located during training. Now let's take a look at the convolution layer hyperparameters. These are the parameters that are used to configure a convolution layer. The first is kernel size. The kernel size is a filter we use to extract the feature from the convolution layer. As we can see in this image, 5 by 5 by 3 is one of the examples of a kernel. Smaller kernels are better, but if it's on the first layer, it takes a lot of memory. The next is stride. A stride is how many pixels the kernel window will slide on the input layer. Normally we use 1 in convolution layers and 2 on pooling layers. The next is zero padding. It is the number of zeros added in an image. Put zeros on the image border to allow the convolution output size be the same as the input size. The next is number of filters. It represents the number of patterns that the convolution layer will look for. Now let's visualize the convolution operation. Here we will see some examples of the convolution window sliding on the input image and change some of its hyperparameters. The first is convolution with no padding and stride of 1. Here we have an input 4 by 4 convolved with a filter 3 by 3 with stride s is equal to 1 and padding is equal to 0. As you can see, the movement of the kernel is 1 because we set the stride is equal to 1 and padding is equal to 0. There is no any external 0 has been added to this layer and it is filtered by a 3 by 3 kernel. The next one is convolution with padding and stride of 1. Now we have an input 5 by 5 convolved with the filter 3 by 3 with stride s is equal to 1 and padding is equal to 1. On some libraries there is a feature that always calculates the right amount of padding to keep the output spatial dimensions the same as the input dimensions. In the next lecture, we will look at the max pooling layer. Thanks for watching. We'll see you in the next lecture. Convolution neural network following individual convolution layers. When added to a model, max pooling reduces the dimensionality of images by reducing the number of pixels in the output from the previous convolutional layer. Let's go ahead and check out a couple of examples to see what exactly max pooling is doing operation wise. And then we will come back to discuss why we may want to use max pooling. On the diagram below, we show the most common type of pooling, the max pooling layer, which slides a window like a normal convolution and get the biggest value on the window as the output. As we can see in the pink block, 6 is the highest value among 4 values, so 6 is selected. Similarly, 8, 4, and 3. It is pooling the maximum value from the 4 values. So it's known as max pooling. The thing to be noted here is that the stride parameter is 2 here because the 2 by 2 filter is moving by 2 units each time. Before getting into the detail, you should know that there are several types of pooling. These includes mean pooling, in which we take the mean of all the numbers which comes under the filter. Then max pooling, in which we take the maximum value from the numbers which comes under the filter. Then we have sum pooling, in which we take the sum of all the numbers which comes under the filter. So why use max pooling? There are a couple of reasons why adding max pooling to our network may be helpful. The first is reducing computational load. Since max pooling is reducing the resolution of the given output of a convolutional layer, the network will be looking at larger areas of the image at a time going forward, which reduces the amount of parameters in the network and consequently reduces computational loads. The next is reducing overfitting. Additionally, max pooling may also help to reduce overfitting. The intuition for why max pooling works is that for a particular image, our network will be looking to extract some particular features. Maybe it's trying to identify numbers from the MNIST dataset, and so it's looking for edges and curves and circles and such. From the output of the convolution layer, we can think of the higher valued pixels as being the ones that are the most activated. With max pooling, as we are going over each region from the convolution output, we are able to pick out the most activated pixels and preserve these high values going forward while discarding the lower valued pixels that are not as activated. Just to mention quickly before going forward, there are other types of pooling that follow the exact same process we have just gone through. Except for that, it does some other operation on the region rather than finding the maximum value. The one last thing we want to discuss is average pooling. For example, average pooling is another type of pooling, and that's where you take the average value from each region rather than the maximum. Currently, max pooling is used vastly more than the average pooling. In the next lecture, we will look at the dropout layer. Thanks for watching. We'll see you in the next lecture. In the tutorial, we will discuss about the dropout layer. A dropout is a technique used to improve overfit on neural networks. You should use dropout along with other techniques like L2 regularization. Below we have classification error. Observe that the test validation error is smaller using dropout. As other regularization technique, the use of dropout also make the training loss error a little worse. But that's the idea. Basically, we want to trade training performance for more generalization. Remember that more the capacity you add on your model means more layers or more neurons, more prone to overfit it becomes. Below we have a plot of showing both training and validation loss with and without dropout. So the question is how it works. Basically, during training, half of neurons on a particular layer will be deactivated. This improves generalization because it forces your layer to learn with different neurons the same concept. During the prediction phase, the dropout is deactivated. So, where to use dropout layers? Normally, some deep learning models use dropout on the fully connected layers, but it also possible to use dropout after the max pooling layers, creating some kind of image noise augmentation. In the next lecture, we will take a look at the concept of one-hot encoding. Thanks for watching. We'll see you in the next lecture. When we do this, the model is usually not interpreting these labels as words like car or trucks. Additionally, the output that our model gives us in regards to its predictions are not typically words like car or truck either. Instead, most of the time our labels become encoded, so they can take on the form of an integer or of a vector of integers. One type of encoding that is widely used for encoding categorical data with numerical values is called one-hot encoding. One-hot encodings transforms our categorical labels into vectors of zeros and ones. The length of these vectors is the number of classes or categories that our model is expected to classify. Here we have a table in which a 0 is represented as a bat and 1 is represented as a ball. If we were classifying whether images were either of a car or of a truck, then our one-hot encoded vectors that corresponded to these classes would each be of length 2, reflecting the two categories. If we added another category like bus so that we could then classify whether images were of car, truck or bus, then our corresponding one-hot encoded vectors would each be of length 3. Since we now have 3 categories. Alright, so we know that labels are transformed or encoded into vectors. We know that each of these vectors has a length that is equal to the number of output categories. And we briefly mentioned that the vectors contain zeros and ones. Let's go into further detail on this last piece. Let's stick with the example of classifying images as being either of a car, truck or bus, with each of the corresponding vectors for these categories being of length 3. We can think of each index or each element within the vector corresponding to one of the 3 categories. Let's say for this example that the car label corresponds to the first element, truck corresponds to the second element, and bus corresponds to the third element. With each of the categories having their own place in the corresponding vectors, we can now discuss the intuition behind the name one-hot. With each one-hot encoded vectors, every element will be 0, except for the element that corresponds to the actual category of given input. This element will be a hot 1. One of the indices for the vector is hot. Sticking with the same example, recall we said that a car corresponds to the first element, truck to the second, and bus to the third. So the corresponding one-hot encoded vectors for each of these categories would look like this. For car, we see that the first element is a 1 and the next 2 elements are 0. This is because each element within the vector is a 0 except for the element that corresponds to the actual category. And we said that the cat category corresponds to the first element. Similarly, for truck, we see that second element is 1, while the first and third elements are 0. Lastly, for bus, the third element is 1, while the first and second element are zeros. We can see that each time the model receives input, that is car, is not interpreting the label as word car, but instead is interpreting the label as this vector 1, 0, 0. For images labeled as truck, the model is interpreting the truck labeled as the vector 0, 1, 0. And for images labeled as bus, the model is interpreting the label as vector 0, 0, 1. Just for clarity purposes, say we add another category, van, to the mix. Now we have 4 categories total. And so this will cause each one-hot encoded vector corresponding to each of these categories to be of length 4 now. The vectors will now look like this. We can see that for each of our pre-existing categories of car, truck, and bus, we still have the corresponding one for each of these vectors in the same places where they were before. The one is first element for car, second for truck, and third for bus. The new fourth element for each of our existing categories is just a 0 since this fourth element corresponds to the van category. Finally, the new one-hot encoded vector for the van category is all zeros except for fourth element, which is a 1, since the fourth element corresponds to the van category. Note that we just arbitrarily said that car corresponds to the first element, truck to the second, bus to the third, and ban to the fourth. But this could very well be in different order. This just depends on how the underlying code or library is doing the one-hot encoding. Now we have the clear understanding of one-hot encoding. We will see the confusion matrix in the next video. Thanks for watching. We'll see you in the next lecture. Let's start with an example confusion matrix for a binary classifier, though it can easily be extended to the case of more than two classes. So here we have a matrix which represents the actual no and actual yes with the predicted no and predicted yes as columns. So what can we learn from this matrix? There are two possible predicted classes, yes and no. If we were predicting the presence of a blue eye people, for example, yes would mean they have the blue eyes and no would mean they don't have the blue eyes. The classifier made a total of 165 predictions. For example, 165 people were being tested for the presence of blue eyes. Out of those 165 cases, the classifier predicted yes 110 times and no 55 times. In reality, 105 people in the sample have that blue eyes and the 60 people do not. Let's now define the most basic terms, which are whole numbers. The first is true positive. These are cases in which we predicted yes and they do have the blue eyes. The second is true negative, in which we predicted no and they don't have the blue eyes. The third is false positive. We predicted yes but they don't actually have the blue eyes, also known as a type 1 error. The fourth is false negative. We predicted no, but they actually do have the blue eyes, also known as a type 2 error. I have added these terms to the confusion matrix and also added the rows and columns total. There is a list of rates that are often computed from a confusion matrix for a binary classifier. First is accuracy. It represents how often is the classifier correct. It is calculated by this formula where we take the sum of total positive and total negative cases and then divide them by the total number of cases. The second is misclassification rate. It is also known as error rate. It represents how often the model is wrong in predicting. The formula to calculate the misclassification rate is the sum of false positive and false negative divided by the total number of cases. It is equivalent to the 1 minus accuracy. The next is true positive rate. It represents the rate when it is actually yes, then how often does it predict yes. It is calculated by dividing the total positive by actual yes. It is also known as sensitivity or recall. The next is false positive rate. It represents the rate when it is actually no, then how often does it predict no. It is calculated by dividing the false positive to the actual no. The next term is true negative rate. It represents when it's actually no, then how often does it predict no. It is equivalent to 1 minus false positive rate. It is also known as specificity. It is represented by the formula 2 negative divided by the actual number. The next is precision. It tells us when it predicts yes, how often is it correct. It's calculated by the formula total positive divided by predicted yes. Next is prevalence. It tells us how often does the yes condition actually occur in our sample. Thanks for watching. We'll see you in the next lecture. Systems more efficiently. There are lots of features of Python which makes it more popular in the programmers community. Let's discuss them one by one. The first one is easy to code and read. Python is very easy to code compared to other popular languages like Java and C++. It is easier to code in Python. Anyone can learn Python syntax in just a few hours, but mastering Python requires learning about all its advanced concepts and packages and modules. Thus, we can say it is a programmer-friendly language. Being a higher-level language, Python code is quite like English. Looking at it, you can tell what the code is supposed to do. Also, since it is dynamically typed, it mandates indentation. The second is expressive. First, let's learn about expressiveness. Suppose we have two languages, A and B. And all programs that can be made in A can be made in B using local transformations. However, there are some programs that can be made in B but not in A using local transformation. Then B is said to be more expressive than A. Python provides us with lots of constructs that helps us focus on the solution rather than on the syntax. This is one of the outstanding Python feature that tells you why you should learn Python. Third is free and open source. Python is freely available and it's open source. This means that its source code is available to the public. You can download it, change it, use it, and distribute it. The fourth is high level and object oriented. As we discussed earlier, it is a high level and object oriented language. This means that as programmers, we don't need to remember the system architecture, nor we need to manage the memory. This makes it more programmer friendly and one of the key Python features. The fifth is portable. Let's assume you have written a Python code for your Windows machine. Now if you want to run it on Mac, you don't need to make changes to it. In other words, you can take one code and run it on any machine. There is no need to write different code for different machines. This makes Python a portable language. However, you must avoid any system-dependent features in this case. The sixth is interpreted. If you are familiar with languages like C++ or Java, you must first compile it and then run it. But in Python, there is no need to compile it. Internally, its source code is converted into an immediate form called white code. So, all you need to do is to run your Python code without worrying about linking to libraries. By interpreted, we mean that source code is executed line by line and not all at once. Because of this, it is easier to debug your code. Also, interpreting makes it slightly slower than Java, but that doesn't matter compared to the benefits it has to offer. The seventh is extensible. If needed, you can write some of your Python code in other languages like C++. This makes Python an extensible language, meaning that it can be extended to other languages. Eighth is Python is a beginner's language. Python is a great language for beginner level programmer and supports the development of a wide range of applications from simple text processing to World Wide Web browsers to games. We will use the Anaconda Python distribution tool for interpretation of our Python scripts. Let's take an example of a simple program and run it on Anaconda platform. Firstly, we need to open Spider installed within Anaconda. Then write a simple program to add two numbers, num1 and num2. We don't need to specify any data type for these variables to store the number. We have set these variables to integer number 10 and 16 respectively, so they will behave as an integer. Then we added them to get summation and store inside the sum variable. Now let's print it to check the sum value. So here we got 26 as an output. One more concept which we need to care about is lists. We will use it in the Python scripts used to capture the data. Lists are just like arrays, declared in other languages. Lists need not to be homogeneous always, which makes it a most powerful tool in Python. A single list may contain data types like integers, strings, as well as objects. Lists are also very useful for implementing stacks and queues. Lists are mutable and hence they can be altered even after their creation. Lists in Python can be created by just placing the sequence inside the square bracket. Let's create some different types of lists now. Firstly, we have a blank list which prints nothing, and then we have list containing the strings. Then we have a list containing different types of object. Similarly, we have common concepts of Python like loops, decision making, etc. One more thing we need to care about while writing a Python is indentation. Like other programming languages, we don't have any braces which specify the code for a particular block. So indentation tells us about a block of code. For example, here we have one example to compare the numbers. Print 9 is less than 14 is a statement which will be executed when if condition becomes true. Check the indentation in this case. With these basic functions, Python provides us different types of packages developed for different purposes. In the coming videos, we will take a look at the NumPy, Pandas, and Matplotlib packages. These packages are necessary to store, analyze, and visualize the data. Thanks for watching. We'll see you in the next lecture. Pandas is built on top of the NumPy package, meaning a lot of the structure of the NumPy is used or replicated in Pandas. Data in Pandas is often used to feed statistical analysis in SciPy, plotting functions from Matplotlib, and machine learning algorithms in scikit-learn package. Pandas basically has three data structures: series, data frames, and panels. A series is one-dimensional labeled array that can hold data of any type: integer, string, float, Python, objects, etc. Its axis labels are collectively called an index. A data frame is second-dimensional labeled data structure with columns same as of the data we represent in Excel. So Pandas data frame is nothing but an in-memory representation of an Excel sheet by a Python programming language. Pandas data frame provides various functionalities to analyze, change, and extract valuable information from the given dataset. In the same way, a panel is three-dimensional labeled data structure. After this conceptual introduction, let's take a look at some of the operations provided by the Pandas on series and data frames. So let's take a look at series first. The syntax to create a Pandas series is pd.series with argument data, index, dtype, and copy, where data parameter represents the data we need to convert to Pandas series, and then index for the series. Dtype is for data type, copy is to copy the data. Now let's take a look at the example of Pandas to create a series from NumPy array. Here you can see the output is labeled series after we pass the NumPy array to pd.series method. Here we have an example of creating series with defined indexes. As you can see, we have mentioned the indices for the series from 100 to 105, and the output will look like this. Notice the difference in the numbering. It changes from 1 to 5 to the 100 to 105. Next is creating a series from Python dictionary. Here we have a list named as data containing student name, age, and gender. When it is converted to the series via the pd.series method, then the output will look like this. Next is data frames. A data frame can contain a Pandas data frame, series, NumPy array, or dictionaries for one-dimensional. Let's go ahead and discuss some examples. From the above outputs, we can tell that our data is a 4x4 table containing 4 columns and 4 rows. We can also tell the data type of each column. Notice that the columns are homogeneous, meaning that each holds a certain set of entries. That is, the grades column only hold grades which are integer. Importing and exporting data. We have learned how to create data in Pandas. But what if you have a dataset that you want to import or export? The dataset could be in any format: CSV, .text, .xlsx, .json, etc. Take for instance a CSV file called pattern.csv containing 365 rows and 11 columns. We can read all the columns and rows in the data variable by using this syntax. The rest of the Pandas operation we will discuss while implementing the Python code. Thanks for watching. We'll see you in the next lecture. Matplotlib package of Python. Matplotlib is an amazing visualization library in Python for 2D plots of arrays. Matplotlib is a multi-platform data visualization library built on NumPy arrays and designed to work with the broader sci-fi stack. One of the greatest benefits of visualization is that it allows us visual access to huge amounts of data in easily digestible visuals. Matplotlib consists of several plots like line, bar, scatter, histogram, etc. We can import the Matplotlib by using this statement: import matplotlib.pyplot as plot. Matplotlib comes with a wide variety of plots. Plots helps to understand trends, patterns, and to make correlations. They are typically instruments for reasoning about quantitative information. Some of the samples plots are covered here. An example for line plot looks like this, where x and y elements are plotted on screen. Here first we have a line plot where we have plotted the x and y lines by using the plot.plot x, y and show it by using plot.show. Similarly, we have a bar plot by using .bar method, and we have a histogram by using the .histogram, .hist method, and then scatter plot by using the .scatter method. So we will use this Matplotlib in our plotting when we train the model. We will discuss about the matplot methods in the coming videos. Thanks for watching. We'll see you in the next lecture. Behind the implementation of a neural network into a microcontroller. These are data capturing, data cleaning and labeling, training a neural network model, convert the model into optimized C code for microcontroller, infer the new data using trained neural network on MCUs. Let's discuss them one by one. In data capturing step, we capture the environmental data via sensors. This data is used to train the neural network. It can be the data captured from the sensors placed to monitor any physical parameter like acceleration, temperature, sound, and visual scene depending on the application. In our case, we will capture the acceleration data via an accelerometer sensor. The next step is data cleaning and data labeling. Usually in first step, we capture the raw data. It can be in hex or binary form or not arranged in such a way so that we can train the neural network directly on it. We need to rearrange this data according to the expectation of our neural network model. We may need to apply some high pass or low pass filters to mitigate the noise from the data. With this, we also know that in supervised learning we label the different data before feeding it to the neural network. So we need to assign different labels to the data we have captured, so that neural network can learn which data belongs to which scenario. We will use a Python script to capture and clean the data in the upcoming videos. In the third step, we will train the neural network on the data we have prepared in the previous steps. We will design a neural network using Keras APIs in a Python script, and we'll separate the captured data into training, test, and validation data to train and evaluate the neural network. After this, we will generate a confusion matrix to know about the accuracy of a model to predict the real scenarios for which it was trained. And then, in the fourth step, we will convert the trained model into the C code by using the ST Microelectronics STM32Cube AI tool. After this step, we can interface the sensors with the STM32 and can integrate the sensor code to the generated C code of trained model, and then we can feed the live data from the sensors to the neural network inside the microcontroller, which has been already implemented in the generated C code of the model. After following these 5 key steps, we can infer the real-time data from any sensor and can perform any real-time action inside a microcontroller and can realize the concept of edgeai. In the upcoming videos, we will take a deeper look into the capturing of data from the accelerometer sensor. Thanks for watching. We'll see you in the next lecture. An accelerometer sensor measures the changes in acceleration in 3 different directions. What is affected by gravity? The accelerometer sensor is an inertial frame sensor. This means that when a device is in free fall, the acceleration is 0 meter per second square in the falling direction. And when a device is laying flat on a table, the acceleration in upward direction will be equal to the Earth's gravity, that is 9.8 meter per second square, as it is measuring the force of the table pushing the device upwards. For acceleration, we usually care about the big changes and want to avoid noise like gravity. Thus, a high-pass filter can help isolate the linear acceleration and a low-pass filter can help isolate the gravity. A low-pass filter can thus be useful for measuring a tilt. For example, in smartphone, rotating the screen is one of the applications based on accelerometer tilt. Unfortunately, any high-pass filter or low-pass filter introduces a delay, which may or may not be acceptable. We will interface ADXL345 accelerometer sensor to our STM32 board and will capture the X, Y, Z axis data via the serial port of the STM32 on our computer in raw form. In our case, we need to capture the vibrational pattern. We are more interested in the linear acceleration produced during the vibration than the gravity. To exclude the gravity, we will use a low-pass filter in our code before feeding the data to the model. ADXL345 is a high-resolution, low-noise sensor and can measure up to plus minus 16 G. We will interface it to our STM32 board via I2C protocol and power it via onboard present 3.3 volt power supply. The data captured from the accelerometer will be sent to the PC via UART pins of the STM32. In the next lecture, we will take a look at the C code for STM32 to capture the data from accelerometer sensor. Thanks for watching. We'll see you in parallel. The timestamp will also start incrementing in the background. The accelerometer data is of 6 bytes, representing 2 bytes for each axis, and 4 bytes data containing the timestamp. Checksum is also calculated with these 10 bytes and sent back to the PC for data integrity. Now let's take a look at the code. We will use the STM32Cube to generate the code and will write an application which captures the data from the accelerometer module ADXL345. So let's get started. Here we have the STM32Cube. Before starting a new project, please check we have the required package for our project. We are using the STM32F4 microcontroller series, so we have already installed the package for it. Now create a new project. Search for the STM32F446RE microcontroller. Here, as you can see, we have the nuclear board. Now start the project. Initialize all peripherals with their default mode, yes. So now we have to configure the pins for our microcontroller. As we know, we have to interface the accelerometer module ADXL345 to the microcontroller by using the I2C protocol. So we need to configure the I2C pins over here. We will use the I2C1 SDA and I2C1 SCL. We don't need these extra pins, so keep it to the reset state. We need this USART-TX and USART-RX to communicate to our PC, and we will send the data from the accelerometer to the PC by using these pins. We also don't need this blue push button over here, so keep it to the reset state, and also keep these pins to the reset state. We have these 2 pins for the external oscillator present on our board. So after the configuration of the pins, we need to go over here. We will look for the USART2 in the connectivity, and here it is. The mode is set to the asynchronous and hardware flow control is disabled as of now. We need a USART2 global interrupt because when we receive the data from the PC, it will be received via the interrupt callback. So we need a global interrupt for it. Now the parameter setting, keep as it is. Then go to the I2C1 and select the I2C over here and keep the setting as it is. So after this, we need to configure the clock over here. We will use the external oscillator, so we need to configure it to highest clock 180 MHz. So it will automatically adjust the clocks for the other peripherals also. So we have completed the configuration part for our microcontroller, and now we need to give a name to our project. So we'll name it as a accelerometer data capture. Set a directory over here. We'll set it to the documents, then select the True Studio as an IDE. Then we have to generate the code. So here we have the generated code. Look for the main file in the source folder. So this is our main file, which is having the 2 handles for I2C and UART. We'll use this handles to control the peripheral of our nucleo board. And here we have some private functions over here already generated. And then we have the whole init, which is basically resetting all the peripherals and initializing the flash interface and sysdig timer. And then we have the configuration of the clock initialized, and then mx GPIO init is used to initialize the GPIO. Here we have initialized the I2C peripheral and USART, and then we have an infinite loop. Before writing the main application, we need to implement some functions. Here we have the accelerometer functions used to initialize the accelerometer, write the settings to the register of the accelerometer module, and to read the values of x, y, and z from the accelerometer module. We have used the whole APIs of the I2C over here to transmit and receive the data. We are reading the values and storing it in the Excel data variable defined over here. The x, y, and z parameters are of 6 bytes. Then here we have a UART-RX callback function. It will be called when UART will receive some data via UART. As we have already discussed the handshaking process, so here we are getting here the 0xFF, 0x00, 0xFF, and 0x00, which is a confirmation code sent by the Python script to the nucleo board. So after this check, a send flag variable is set to the 1. In the else part, if the confirmation code has not been received yet, it will send the received data back to the user and convert the timestamp from the bytes to the integer and store it in the timestamp variable, which is a uint32_t defined in this file. Then we have an increment timer function. When the confirmation code is verified, this send flag is set to 1, and then timestamp will start to increment by 1. This function will be called in this file over here. This function is called by the sysdig ISR at every 1 millisecond. So it will run background and call the increment timer function, by which this timestamp will start incrementation. So in the main code we have already discussed, it has initialized the whole and other libraries. We have also initialized the accelerometer module over here, which has been defined over here. Then we have enabled the UART interrupts. So here we have send flag is equal to 1 now. And then accelerometer accel read values will start reading the 6 bytes of data from 0x32 register and put it into the Excel data variable. After this, a timestamp will be converted back to the byte 4, which is stored in the TS buffer. After this, we calculate the checksum of all the bytes, these 4 bytes of timestamp and the 6 bytes of accelerometer data. Then we have given a delay of 1 millisecond over here, and then we transmit the 6 bytes of accelerometer data via UART, and then 4 bytes of timestamp and checksum. So we have 6 plus 4 plus 1, 11 bytes of data, which is sending continuously to the Python script. A Python script will decode this data, and Python script will capture and store it in a binary file. Now let's run and check it. We will program our board. We have already connected the nucleo board to our PC. As you can see, this is listed over here, STM32F446. Now browse for the binary file. Erase the chip first to make sure the flash is empty. Then start the program. Once it is completed, disconnect the board and check it on serial terminal. Check the COM port by going to the device manager. it's comp5. Open it. Firstly enable the hex, and then now suppose we have to send a timestamp of 4 bytes 1, 2, 3, 4. So here we have sent it, and we have received the same data from the microcontroller. Then the next process is to send the confirmation code, which is FF00FF00. Once we send this, a lot of data starts to coming from the Nucleo board, which is actually 6 bytes of accelerometer data, 4 bytes of timestamp, and 1 byte of checksum. So we will capture this binary data in the Python script and store it in a file. We will go through it line by line. Firstly, we have defined here the macro for the I2C address of our accelerometer module. Next, we have handles for the I2C and UART peripheral, and here we have defined some static variables we have used in the code. Next is the prototype declaration of some local functions. Here we have defined functions to read and write the values into the register of the accelerometer, and accel_init function is used to initialize the accelerometer module. All the values of the registers and their address have been taken from the datasheet of the ADXL345 module. Next we have UART receive interrupt callback. This function will be called whenever data reception will happen from the UART. More specifically, as we have talked regarding the handshaking process before, if we understand this function by keeping that in mind, then it is something like this. When the Python script will send the timestamp, a receive interrupt will be generated and this function is called. It will send back the same bytes it has received. Python script will then check for these bytes. If these are the same as sent by the Python script, then Python script will send the confirmation code as FF00FF00. Then it will set the send flag variable to 1. Afterwards, it will go to the infinite while loop defined in the main function. One thing to note here is that GPIOs, I2C peripheral, UART, and accelerometer modules are initialized. Once the send flag is set to 1, microcontroller will start reading the 6 bytes of data from the accelerometer and convert the current timestamp from integer to the bytes so that it can be sent via the UART packet. This timestamp is continuously incremented by the tick function defined in the STM32F4XX hall.c. This function is called every 1 millisecond automatically in the background. After this, we have calculated a checksum and sending these 11 bytes to the Python script continuously. In the next lecture, we will take a look at the Python script we are using to capture the data. Thanks for watching. We'll see you in the next lecture. Information code is defined which contains 255, 0, 255 and 0, which notifies the microcontroller that handshake is successful. A SCQ list is to capture the raw accelerometer data. And then we have a char which is empty as of now, and this char is basically read from the input command file .text, which is actually to control the capturing process. The concept is we have here the input command file in the same directory as of the script. We have defined one value over here, 2. So the Python script is continuously reading this file and checking the value whether it is 2 or something else. When this value is something else than the 2, then the capturing process will continue. But if it's set to 2 and saved, then the capturing process will stop. We will see it later how it works. Then we have defined over here the integer to bytes function, which converts the integer values to the bytes, and here we have a function to convert the bytes to the integer. Now the Python script starts from here. Here we have an object known as serial, which is having initialized with the port COM6 and baud rate of 9600, timeout set to 1. Then we are getting the timestamp via the time.time function over here, and we have subtracted it from some constant to make the size of the timestamp shorter so that it can fit into the 4 bytes, and it's easy to send 4 bytes to the Nucleo board as compared to the larger bytes. Then we have converted the timestamp to the bytes and sent those timestamp bytes via serial port to the Nucleo by using this method. After this, our infinite loop starts over here. After sending these bytes, as we know, the Nucleo board will send the same bytes to our Python script, and we are getting the size of the received bytes in this variable and checking if the size of the variable is greater than or equal to 4. Then we are reading those bytes and storing it in the RCV list, and we are checking if the sent bytes is same as of the received bytes. Then it will send the confirmation code to the Nucleo board again and will print handshake is successful, and it will break from this infinite. So after this, we have this infinite loop in which we are capturing the data coming from the serial port. Here we have a for loop which is continuously reading the port and appending the received data to the SEQ list. In this statement, we have opened the file input command file.txt, and we are reading the first character of the file and storing it in the char variable. We are checking for this char variable. If it is set to 2, then the data capturing will interrupt and this infinite loop will break. After this, we have this byte array function which is converting the SEQ data to the byte array and storing it into the S. And then we have to save it into a raw accelerometer data file, which is a binary file, and here we are writing the data to the file, and finally we are closing it. Now let's run the script and see what happens. So here, as you can see over here, the handshake is successfully done and data capturing is in progress now. So it is capturing those 11 bytes and storing it in a binary in a sequence list. Now to stop the training process, we have to change the number in this file to 2. So here we have interrupted the capturing process and data is saved to the file. Now let's check the file saved. Here we have the raw accelerometer data file. Which is having this binary file, so we cannot read in the notepad. So that's all about the capturing process via the Python script. In the next lecture, we will label and organize this data so that we can feed it to the neural network. Firstly, we have imported the time and serial Python package, and then we have defined RCV list to store the timestamp received from the microcontroller. Conf code is defined to store the confirmation code, which we will send to the microcontroller after the handshake process. A SEQ list is defined to capture and store raw accelerometer data. Here I want to highlight one point, that we are using a text file to notify the script when to stop the capturing of data by setting a character value in it. Next, we have defined some methods to convert integers to bytes and bytes to integer. After these functions, our main script starts here. Here in the first line, we have opened the serial port to which our STM32 USB has been connected. We can check the port number by opening the device manager in Windows. The baud rate for transmission of data is set to 9600. Then we got the current timestamp by the time.time method and multiplied it to 1000 to remove the decimal points and subtracted some constant value so that we can convert this integer value to bytes. It fits into 4 bytes. We don't want to send larger bytes for handshaking. In the next step, we convert timestamp to bytes and stored in timestamp_bytes. Then we send the 4 bytes via serial port. Then we have an infinite loop in which handshaking process with the microcontroller has been performed. After sending the 4 bytes via serial, these 4 bytes will be sent back by the microcontroller, and we will monitor the number of bytes received by port.inWaiting method. If received number of bytes are greater than or equal to 4, then we will read the number of bytes and store in RCB list. If received bytes are equal to the sent bytes, then send back the confirmation code we have defined in the beginning of the code to notify the microcontroller that we have received what we had sent. With this, the handshake is successful. Next, we have the infinite loop to capture the data sent via the microcontroller. As we know, the microcontroller is sending 6 bytes of accelerometer with incremented timestamp of 4 bytes and 1 byte of checksum. We are capturing and appending it to the SEQ list. With this, we are continuously reading the input command file.txt. If we receive the character 2 from the text file, the data capturing will be interrupted and the infinite loop will break. After this, convert the captured data to the array of bytes so that we can write these bytes to the binary file. A binary file raw accelerometer data file has been opened in binary mode. Then, by using file.write method, data has been saved to the file and then file has been closed. So this was the whole process of data capturing in the raw binary form. In the next step, we'll do the labeling and cleaning of the data. Thanks for watching. We'll see you in the next lecture. A machine, motor, or any object from which data needs to be collected. The second row represents the vibration pattern of the motor in a particular state. Suppose vibration pattern 1 where motor is in a normal state and vibration pattern 2 where motor is in a fault state, and vibration pattern 3 when motor is in a high fault state. The third row represents the timestamp when the sample of x, y, z has been collected. The last 3 rows represents the g value of x, y, z axis of the accelerometer. So we are clear with what we have to do now. Let's see the code implemented to convert our binary file to the labeled and organized data. Here we have defined the lists and variables used in our program. Then a method which converts bytes to the integer. Now in first statement of our Python script, we have opened the raw accelerometer data file in binary read mode. In the for loop, we are reading and appending all the binary data in sequence list. Then we have stored the length of sequence list in length of list variable. Just to be safe, we have discarded the last 11 bytes from the data by subtracting the 11 from length of list. Then in while loop, we are looping on each 11 bytes of sample till the end. As we know from the previous lecture, 6 bytes containing x, y, z value, 2 bytes for each, 4 bytes for timestamp and 1 byte for checksum. So in the while loop, firstly we are calculating the checksum of 10 bytes, stored it in the A0, then compared the received checksum which is stored at the 11th byte of the frame. If it is equal, then print data sample is accepted. Then we store the timestamp bytes in a separate list from the received sample and converted the timestamp bytes to the integer and stored in the timestamp variable. Offset is also added again, which we subtracted while data capturing. After this, we took the 6 bytes sample of accelerometer bytes and converted it to the numerical form, and then we converted these values to the g values and stored in xg, yg, zg variable. Before starting this script, we also need to mention the pattern ID. It will remain the same in all cases if the data collected is from the one object only. Then we have to give pattern name. It depends on the condition of the object when data was collected. Suppose we gave pattern name normal when data was collected in normal condition of motor, and faulty when data was collected in the faulty condition. Then we appended timestamp xg, yg, zg, character, carriage return, and new line. This sequence will be joined in the joined sequence list. If checksum is not correct, then we will discard the sample. We have traversed 11 bytes in each iteration of the while loop because we have 11 byte frame containing data for one sample. In the next step, we are saving the list in which we labeled and filtered the data. One thing to note here is that at one time we can only label and filter the data for one type of pattern ID and pattern name. In the next time, when we will filter the data from different binary with different pattern ID and pattern name, the labeled sequence will append to the same text file. We can also use NumPy arrays in these scripts in place of lists. NumPy arrays are a lot faster than Python list, but for the educational purpose, just to make a practical uses and to show how we can use Python list, we made these two scripts using list. We will use NumPy arrays in the next Python script main app.py. In this script, we wrote code to train the neural network. Now let's run it. So here, this is the data we have saved to the file. And here we have X, Y, and Z data over here. You can also check the file accelerometer labeled data in which we are getting this labeled data. So in the next step, we will build a neural network and a Python script to train it on the labeled data. Thanks for watching. We'll see you in the next lecture. Sequential model with one input and output layer and 4 hidden layers of convolution 2D, max pooling 2D, flatten, and dense respectively. Let's visualize what happens inside this model of a neural network while training and prediction. Here you can see different layers present in the network. Let's go through them one by one. Firstly, we have input layer of 24 by 3 by 1. We have 24 rows, 3 columns, and 1 number of channels, with padding is equal to the 0. These rows represents the X, Y, Z axis data captured from the accelerometer. Then a convolution 2D layer of 16 by 1 is convolved with the input layer with stride is equal to 1. Means when we will move the convolution 2D layer while convolving with the input layer, it will move by one element. We already discussed about stride in the convolution operation based lectures. We have set the filters to 24 to extract the different features from the input layer. So we will get 24 9 by 3 matrices as an output. Then a 2 by 1 max pooling hidden layer has been added to it. After convolving it with the output 1, we will get the 24 4 by 3 matrices. Then we have to perform the flattening operation on this output, by which all the elements present in the output 2 will rearrange itself to a single column. So if you multiply 4 by 3 by 24, we will get total 288 elements in the single row. Then we have added a dense layer of elements 12, which will make a fully connected layer with the previous 288 outputs. In fully connected layers, all the neurons are connected to one another, as you can see the 288 elements are connected to one element of dense layer. Similarly, we can imagine for all the elements. Next, we have last layer of dense with 6 elements, because at last we have to predict the output for 6 classes. Now we have seen the architecture of our neural network. Let's see how we can implement it using the Keras APIs in Python code. So here we have defined the functions for our model as a training model. A sequential model is created named as model. Sequential is just abbreviated as the sequence of layers. The next step is to add layers to this model with all the expected parameters. The first layer is convolution layer with 24 filters and 16 by 1 kernel size. The input shape to this layer is of 24 by 3 by 1, and activation value is used to make it non-linear output. So these parameters we have to pass here in the Convolution 2D API of Keras. Next we have to add a pooling layer of size 2 by 1 with stride is 2 by 1. Max pooling 2D API has been used to do this. Next we need to flatten all the outputs generated by adding the flatten API. Then we have added a dense layer of 12 elements with ReLU activation function. A dropout layer is added to minimize the overfitting of the network. On the last dense layer, change the number of nodes to the number of classes in your data, means 6, and set the activation to softmax. In this instance, we set the softmax because it models the fact that labels are mutually exclusive. One and only one of them is right. As we can see, the hidden layers are more than one in this network, so we will call it deep neural network. Then we have to set Adam optimizer algorithm for the training of our algorithm with learning rate of 0.001 and decay of 1 raised to power 6. Model is compiled by using the categorical cross entropy loss and matrices as accuracy. In the next lecture, we will discuss the methods used to prepare 24 by 3 by 1 input layer from our labeled data and how to feed it to our neural network for training, testing and validation. Thanks for watching. We'll see you in the next lecture. We have implemented our neural network model using these layers. We also need optimizers algorithms to train our model, so we need to import it too. Then we have imported our supporting functions as SF identifier. These are the functions we have defined in the supporting function.py file to plot and read the data from the text file. Then we have set the threshold of printing data to console to maximum value to avoid the loss of data on console while printing. If we skip this step, then our console would not show the old data in case it's huge. We have set the random seed to 611. It is the input value used to see the pseudo-random number generator. Then we have specified the ggplot style for plotting with Matplotlib. Finally, our main code starts from here. We have used read data function from our supporting functions to read the data from a text file to the data set list. To check the output of our step by step, we have written here some test code. We have printed the dataset over here and then defined an empty infinite loop. Let's uncomment it and run the script. As you can see here in the console, it has given the labels to each column we have defined in the supporting function.py file and assigned the low number for each row. We can also visualize the data stored in the variable explorer. As you can see, the data in the dataset variable is same as we printed on the console. In the next step, we have to pick the 180 samples from each type of pattern and plot it on a graph. Before that, we need to know the different types of patterns present in our data. Let's print this test code and check the output. As you can see over here, it has printed the 6 labels as fault 1, fault 2, fault 3, fault 4, no operation and normal. Now we have to loop around these 6 labels and pick the 180 samples and plot it using plot vibration pattern function from supporting function.py. Let's print the data for fault 1 pattern only. Uncomment this test code and check the output here. Here it has printed a group of 180 samples randomly picked from the dataset. Check the size here in the variable explorer. It is 180 by 6. Similarly, in next iteration of the for loop, it extracts the 180 sample for other labels and will plot it. Now let's comment the test code and run it again. Here you can see the output. It has plotted the data for X, Y and Z for each pattern label. Our next step is to segment the data into 24 by 3 sample window to feed it to our neural network. Here we have used the split data function from supporting functions and passed the dataset variable into it. This function returns us the 2 output variables. segments, and actual labels. Now let's print and check the output. As you can see over here, it has created 2236 blocks of 24 by 3 window and also stored the 2236 labels corresponding to each window block in actual label variable. As we have already discussed, the concept of one-hot encoding is assigning a binary label to each label present in our data. This step is necessary because while training a neural network, we need to assign the outputs in one-hot encoding labels in the model.fit function. Now let's print the output and see what happens. As you can see here, it has assigned a binary value to each label. Let's check in the variable explorer, in which it has assigned 000001 to all the normal labels and 100000 to all the fault one labels and 010000 to the fault 2 label. Similarly, we can check for others. In the next step, we have to extract the number of rows and columns of a window from segment by using the shape method. Segments.shape1 will return us the number of elements in segments variable at second position, which is 24, as you can see in the variable explorer. Similarly, we can extract the number of columns in window, which is 3. We have specified the number of channels as 1 because we have a 24 by 3 window only. In case we need to extract the features from a colorful image which is having dimensions 24 by 3, then we need to specify the number of channels is equal to 3, because in a colorful image we have to extract features from the R, G and V component of the image. I hope now you understand why we have only one number of channel. Next, we have specified the number of filters, number of rows in the kernel, and similarly we have defined parameters for pooling layer, dense layer and output dense layer. In the other parameters, we have defined the training data split ratio to 0.8. It means we have to split the dataset into two parts, training and test data. Training data is the 80% of the total data, whereas 20% of the data we will use for testing purpose. We have defined the number of epochs to 10, means we will train our neural network 10 times with the same data. And batch size is set to 10, means in a single epoch out of the total window it will take 10 windows of 24 by 3 by 1 at one time to train the network. Next, we have reshaped these segments of 24 by 3 to 24 by 3 by 1 to feed it to the neural network, because we have specified the number of channels as 1. Now let's print the output. As you can see in the variable explorer, it has added one more dimension to the segments and stored it in the reshaped segments. Take a look at this. Next, we have to split the data into training and testing. We have used the numpy random.rand function, which generates the random numbers between 0 and 1 with equal probability distribution, which means we will get the uniform random numbers in the range 0 to 1. We have to generate the random number equal to the number of 24 by 3 by 1 segments, which is 2236 as of now. And then we have compared the generated random numbers to the 0.8. If the generated number is less than 0.8, then it returns true, otherwise false, which means we will get 80% times true and 20% false out of the total number of segments. So here we have got 2 to 36 times true and false. Next, we have to put the training and testing data in different variables. Pass the train split to reshaped segments variable. It will automatically discard the false elements and will keep only the segments which are true. Then we have to convert the not a number elements to the numbered elements. Now let's print it. And we can see here in input training data variable which contains only 1816 segments out of 2236 segments. Similarly, we can get the output labels of training data corresponding to each segment. Then we have to extract the input and output test data in a similar way. But we have to pass the opposite of the train split data so that the true values becomes false and false becomes true. After printing, we can check test data got 420 segments out of 2236 segments. Then here we have defined the training model we discussed in the previous lecture. Now we have to train and evaluate it on the training and test data respectively. Firstly, we have to create an object of the training model. Then print the layers present in the model. To start the training, use model.fit and pass the input and output training data. Then pass the validation split, which is 1 minus training split ratio. Pass the number of epochs and batch size. Verbose is equal to 2, which means it will print the number of epochs done while training. Then we have to evaluate the model on input test data and output test data and get the accuracy of our model print. Print the error by subtracting the accuracy from 100. Then save the model and also save the input and output test data in .npy format. We will use this data while plotting the confusion matrix. Thanks for watching. We'll see you in the next lecture. So let's get started. Firstly, we have imported the required packages. Then we have to load the model test data and ground truth data, means test output data we created in the previous lecture. We can check these variables in the variable explorer. Then we have created a numpy array to store the labels for row and column of our confusion matrix. Then run the model.predict method on the test data and store it in the predictions variable. We can check the predictions in the variable explorer. Here you can see the prediction made for 1 and more close to 1 than in normal case. So it turned to blue. Similarly, we can check the output predicted for each class by scrolling it down. Now we have two variables, predicted class and ground truth class, containing class equal to the number of columns in prediction variable and ground truth variable. You can check the size of both of them in variable explorer, which is 420. In the next step, we have to find out the column number containing maximum number in each row for prediction variable and ground truth variable. Then store results in the predicted class and ground truth class. Then create the confusion matrix between the ground truth class and predicted class. We have to normalize it before printing. And then append the labels to the row and column in the confusion matrix and check the output while running it. As you can see over here, we have got the 100% correct predictions for 1 parameter, whereas 85.45% for normal label. It predicted the wrong outputs in column 2 and 3 and 4. So by analyzing this confusion matrix, we can analyze the performance of our model. In the next step, we will generate code by importing this model to the STM32Cube Thanks. So here we have our generated code. In this video, we will take a look at how to modify the files and which code to include to capture the data from the accelerometer and then feed it to the model generated via the STM32Cube to infer the results based on it in the real time. So let's get started. Here we have two files modified, apexcubeai.c and dataprocessor.c. The rest of the code is the same as generated in the previous video. So here we have got two functions, AI init and AI process. AI init is used to initialize the peripherals and other initialization functions, and then AI process is a continuous running function which is actually collecting the data and inferring that result based on it. Here, as you can see, we have used the accelerometer functions implemented in the previous video, and then we have initialized the accelerometer peripheral here, and here we have a data init processor, which is actually initializing the neural network. And then we have the AI process function. In this function we are reading the values of x, y and z, and then converting these bytes to the integer form and storing in the x, y and z. And then we have multiplied these values to the 0.039 to convert it into the unit meter per second square, means acceleration. So then we have stored it in this structure. As you can see over here, we have the structure. It is having the float x, y and z to store the accelerometer values. And then we have here the 50 milliseconds of delay, and then we have passed this structure to the data infer function, which is defined in the data processor.c. It then performs the inference on the data and then gives us the output over here. Based on the output, we have printed here the fault 1, fault 2 or fault 3 or is normal. Let's look into the data processor.c. Here we have basically three main functions: data init processor, data infer and data get result. Data init processor is initializing the neural network and enabling the CRC clock for using AI library on the STM32. Data infer is the function which we have used to run the inference on the collected data via the accelerometer. Thanks for watching. We'll see you in the next lab. And here we have a multimeter which is actually measuring the dropped voltage. Right now it is 1.73. So as we will increase the voltage, we will see the difference on the serial terminal output. Now you can see we have the output on the serial terminal. It is normal right now. So let's increase the voltage right and check the output. So by increasing the voltage, as you can see on the serial terminal, we are getting right now fault 3. So it is in the state where we captured the fault 3 data. Right now it is inferring the same results and giving the output on the serial terminal. So let's increase it more and then check. As you can see, it is changed to fault 2 right now. Let's go back to the normal again. So here we got the normal. And I have increased the voltage again, and the fault changes to the 3. So in this way we can infer the results in the real time. As you can see over here, we are judging the state of the machine via sensors without establishing any electrical contact to the machine. That's why the solution will be more reliable and long lasting. I have trained the neural network on my setup. Vibration pattern may vary in your case. You can use the same neural network, but you need to train it on your setup to get the maximum accuracy. Thanks for watching. The output may vary in your setup because the neural network was trained on this setup right now.